Hi, everybody. It's a pleasure to welcome you to this live interactions session. And this is perhaps, I think, the third time I'm teaching this course. So it's very good to be with you once again. Many people have already sent in their wishes. So Manvi Jain, SM, good evening to you both. ABCD, good evening to you also. And thank you, Sridhar, for putting out that instruction. So I think if you have any questions that you would like to discuss, please feel free to put them here. I will try to answer them to the best of my capacity. So there was a sheet which was shared already, and there are some questions in the sheet, but those are, like a question bank. There are 4 or 5 questions, so I'll keep them. And we can, if there are any questions which come here, I would like to take them first. And then if there is nobody asking questions here, we could go through those questions. So that is something we can do. I hope you are enjoying this course. So Hani Barak, thank you. Good evening to you also. ABCD has asked something. Okay, so he or she is asking whether we can please outline the group and rings which we touched upon in lecture 25. Explain the theorem in the same lecture when you stated that group UP have primitive elements. Okay. So, all right. So, what is a group? Good evening, Fazila. What is a group? Group is basically a set. So, meaning I could also tell you some background and some stories about it. So, the whole question is motivated by being able to solve equations of the type AX equal to B. I don't remember if this is what I have given the background in my lectures, but this is what it is. Utkarsh, good evening to you also. So Ax equal to B, this is this equation we would like to solve in a set, okay, where A and B are elements in the set, and for X we would like to solve. Mohini, good evening to you also. So the thing is that we would like to bring the A from this side. So, the usual answer to Ax equal to B should be X equal to A inverse B. That should be the answer, correct? Meaning we all know when you want to, for instance, if you are working with integers and you are asked to solve for a plus x equal to b, your natural thing would be to say that x is minus a plus b. Up you are adding something to a and you are getting b. So to get x, that's something which you want to solve for, should be the difference of b and a. So when you are talking about multiplication, it would be the inverse of a multiplied to b. That is what it would be. So the group should be a set where you would have some way to invert elements. Okay, so if we are trying to say x equal to a inverse b, you will say a in, you would then when you want to verify a inverse b is one element, and you want to multiply to a by a inverse b and check whether you get b as the answer. So a, which is one element, and a inverse b, this is product of two elements. When we take the product of these two, okay, once again, when we have a and we have a inverse b and we are taking the product of these two, there is a bracket for a inverse b because it's a product of two elements and a is a separate element. So it's a bracket a inverse b bracket complete. But what we use is that there is associativity in the product. So a group should be somewhere where there should be a closure property. When you have two elements and you take, there is some way to define the product, you get again an element in the same set. This is the first notion of group theory. Second thing is this associativity property, which says that if you take A and then take product of two elements B, C, this is same as AB into C. Okay, so the product A into BC is same as AB into C. This is the associativity which we can use here. A into A inverse B will become A inverse into B. And now that A inverse by our property of the inverse, which will be an axiom again in group theory, should be identity element. So there should be the identity element which when multiplied to every element should give you that element back. Okay, so once again, the four properties of a group. First of all, it should be a non-empty set and there should be some kind of an operation defined on it. So you should be able to, get two elements, take two elements and get one more element out from this. One more meaning it's just an element in the set. It doesn't have to be a separate element, a third element. Okay. So this is the closure property. Then there should be associativity. A into BC is AB into C. And then we need to talk about inverse and identity. But to talk about inverse, we should know that there is identity. So identity action should come before the inverse action. So we say that there is an element E with the property that E into A equal to A into E equal to A for every element A. And then we say that there should be an inverse. So this was in response to question asked by ABCD about groups. In rings, what we have is that there is the underlying group structure, which is an abelian group structure, which we denote by addition. And then we put a product. So there is an addition and a product. So there are two operations, addition and product. And we tie these up by saying that there should be distributivity, meaning A multiplied to B plus C should be AB plus AC. This is the way. So B plus C is addition and you are multiplying by A to that. This should be same as A into B, A into C, and the addition of these two. And similarly, the other way, which will be A plus B into C, should be AC plus BC. So this was about groups and rings. And then I said that the group UP has primitive elements. So what is UP? UP is the set of all those integers which are less than P. So you start from 1 and go up to P minus 1. And among them, you take those. You will take elements which are prime to P, co-prime to P, but since P is a prime, all these elements will come. And then we said that there is a primitive element, which means that there is an element which will generate the whole thing. It's a cyclic group. That is what one means by saying that it's a cyclic group. So explaining the proof of the theorem will be a bit difficult here. I suggest that you go through the video once again. If there are any particular steps which you haven't understood, then please ask. By the way, I must tell you that there are two mailing lists. There is one announcement list. You by default get all those emails which are sent to the announcement list. There is another list which is called discussion for this course. So people can ask all kinds of questions in the discussion and we try to answer as many of them as possible. So this was ABCD's thing, and then I think up to Fazila, Utkarsh and Mohini I have explained. Sir, please discuss question number 10 of assignment 4, week 4. Good. I will do this. Fazila, I would like to, keep also people interested. So there are already also some questions in this sheet. What we would do is that particular questions we could take towards end. We have to keep this for 1 hour. What would typically happen, because I have been doing this for 2-3 years now, is that people may come late. And then they will say that, oh, please discuss this question, which we would have discussed already. So perhaps it is better that we wait for 10-15 minutes, see if there are anything else. Otherwise, we will go through these questions one by one. Anshu, good evening to you also. All right. So Utkarsh has a question which can be discussed. Simultaneous linear congruence का solution निकालने में problem आ रही है. So in fact, there is an algorithm that we have given. And the algorithm will tell you how to compute solution. What may happen is that these numbers are really big. But what is expected is that you will have some 10 problems to be done in a week, typically, meaning you will get more than a week, you will get 10 days or something. But I know that the next assignment will come again on the next weekend. So you get about a week to solve all these questions. So what you could do is to use calculators, meaning these are big numbers. I really don't expect you to, do everything on slate or on a notebook like Ramanujan did. That's not what I expect you to do. So what you should do is that, first of all, find prime numbers dividing the number. If you can find the prime factorization of your number, then things become much more simple. So that is the basic thing that you should try to do. And then finding, given an element, if you can find an element which is the inverse of that element. Suppose there is x given and there is a capital N, and if x is co-prime to capital N, you should be able to solve for xy equal to 1 modulo n. If you can do that, which is the calculation that is required, once that is done, then everything else is simply multiplication. So solving the, using Chinese remainder theorem, simultaneous linear congruence, as we all understand, it's really solving that you have one particular solution one particular number which is congruent to 1 modulo one of those and 0 for all others. So that is the only thing that you have to solve by hand. Once you solve by hand that particular problem, then everything else becomes easy. So please try that. All right. So Facts has asked, can you please explain Euclidean algorithm? Yeah, sure. So Euclidean algorithm, interestingly, this holds also not just for integers, but it holds for some higher rings as well. So what does it say? It says that given two numbers, so this is something, which is very standard. First of all, we have been studying the modular arithmetic. So for instance, whenever we have some number, let's say 2024, the current Gregorian year, and then there is the number 10. Okay, and we say that 2024 is congruent to 4 modulo 10. So what it really means is that the 2024 minus 4 is divisible by 10 because it's 2020, right? That is divisible by 10. So what we have used here is that given this number 2024 and given this number 10, we have written 2024 as a multiple of 10 plus a number which is smaller than 10. Okay, and this can be done for every number a and n, and q. Q is that quotient. Q is the number which divides n. Wherever q is non-zero, you can write every n as aq plus r. R is the remainder, where r is strictly less than q. And once you demand that r is between 0 and q minus 1, it can go up to q minus 1, but it will not go to q. Once you demand this, then we see that there is a uniqueness property here. Because you cannot have two numbers which are between 0 and q minus 1 and yet their product is divisible by q. That can happen only when they are same. So we get a uniqueness for that. Okay, so Euclidean algorithm basically says that whenever you have n, which is any integer, and q is a natural number, then you can write n as a times q, a multiple of q, plus r, where r is positive. So it is bigger than or equal to 0 and is strictly less than q. That is the Euclidean algorithm. It also holds for polynomials. You should check it for polynomials and see, you can check on Google Euclidean algorithm for polynomials, and it gives a new set of rings called Euclidean rings. It's a very interesting study in algebraic numbers. So Shasya has asked, can I submit the assignments I missed? So unfortunately, that is not allowed. NPTEL has some policies, and among the policies, the thing is that once the last date for submitting assignments is over, then we do not allow the assignment submission. However, the thing is that, for 12 weeks, we will have 12 assignments. And when we compute your final score, there are some 3-4 least scored assignments are ignored. So we don't look at all 12 assignments and check the marks. We look at only the marks for some top 8, 9 or 10 things. I'll have to check that correct number. But if you miss out on some, it is okay. I think assignment 4 was to be submitted yesterday and assignment 5 is still ongoing. Assignment 6 will go live very soon. So I think even if you can start with this, it will be good. You can go on with this. Okay. Okay, so Shasya has said that. Srinivasan, a very good evening to you also. Shasya, I have responded to your question. Kaustubh Kamri, can we follow along with this entire course without being well versed in abstract algebra? Of course, meaning that's the whole point that, even if you don't know abstract algebra, if you are able to take some statements as black boxes, if you are able to take some statements as something which is granted, you agree that these statements are correct, and then you want to proceed with that and try to see if you can solve some questions, then you can definitely learn this course without being really, good in abstract algebra. Sanjeev Karji, pranam to you also. So Shasya says, actually, I missed the assignment due to heavy course load of my college. Yeah, I know. Colleges can really give very heavy loads, so I do understand that. Sanjeev says, please be available on homomorphism. Homomorphism, what is homomorphism? Is that a website or something? I think, Sanjeev, you will need to explain more. Fazila says, but sir, calculators would not be allowed in the examination hall. Okay, I think, examination is typically online, and the computer where you are supposed to enter the marks has an inbuilt calculator. So this is quite okay. Of course, the what is true is that, in the assignments, we will prepare you to work hard. And so therefore, we will give you some difficult questions. But typically in exams, there will not be questions which will have 4-digit numbers or 5-digit numbers. Okay, so Fazila says, so how can we solve for big numbers? The practice is the only thing, Fazila, meaning, here you haven't really given a precise particular question which you would want to solve for a big number, but I am assuming that we are going along with the Chinese remainder theorem, which is solving simultaneous congruences. So there again, as I said, the main trick is to invert an element modulo and n. I think if you are able to do that, which is also done again modulo primes. So if you know some primes and if you can work with the primes, then I think that would be easier. SN says, please explain the fundamental theorem of arithmetic. Okay, right. So fundamental theorem of arithmetic says that every natural number can be written as a product of primes. Okay, so first of all, we have to say that there are two parts of this. Number one says that you can factorize a given number as product of primes, and then the second part will say that this factorization is unique. So what do we mean by uniqueness? Suppose we take some number like 36. So we will say whether 2 divides it, whether there is a prime, we start with primes and try to divide it by 2. 2 divides 36, so you can write 36 as 2 into 18. Then 2 is a prime which cannot be further decomposed, so we look at 18. 18 can be written as 2 into 3, right? So 18 can be written as 2 into 9. So you have 2 into 2, and then there is this 9, which can further be written as 3 into 3. So what we do is that actually, if you know how to decompose all numbers up to 36, then we prove that 36 can be decomposed. So this is what is called the method of induction. So what we do is that once you are given a number n, the case 1 will be that n is a prime. And if n is not a prime, if n is prime, we have the decomposition. N equal to p, the particular prime, that is the decomposition. Right? So you have the decomposition for n equal to p. Whenever n is a prime, we have the decomposition. Now, if n is not a prime, then it should have a factor. What is our definition of a prime? Prime is the one where there has to be, for prime, there is no factor between 1 and p. 1 and p are the only factors, positive factors. But if n is not a prime, then there has to be a factor. So there is an a which divides n. And once a divides n, you can write n as a into b. This is our very definition of factor. Correct? So you have written n as a into b, where a is bigger than 1, b is bigger than 1, because you are assuming that n is not a prime, so you have a factor in between. Now these both a and b can be written as product of primes because you are using induction. So a and b are both less than n, they are product of primes, and once you put those two products next to each other, we have that our whole n is a product of primes. Okay, this is a very quick proof of showing that every natural number is factorable. Now, after this, we would want to show that whenever there are two ways to write it, then the primes occurring on both the factorization should be the same with the same multiplicity. That's a proof which is slightly involved. So for that, I will request you to go to slides and go to the lecture video and check it again. It's done in complete detail there. Okay. Krishnan Nayyar Sashi Kumar says, what about the collards? And for where p is the immediate predecessor of n as number sufficiently large. I don't quite understand what he means by collards. Capital N is 2 power n, 3 power n, 5 power n, up to so on. So we are taking product of this, where p is the immediate predecessor of n as number sufficiently large. Krishnan Nayyar, please explain your question. Could you please give me a catch-up David Anand is asking, could you give me a catch up on modular arithmetic if possible? Sure. So what happens is that, many times we want to know whether some solution is possible. Say, for instance, if I want to know whether 2 divides the number 2023. And, meaning typically if I ask you this question, does 2 divide 2023? You will immediately say that no, the last digit of 2023 is odd. 2 cannot divide it. So what we have seen here is that multiples of 2 are the ones whose last digit must be even number. Correct? So in other way, suppose we are looking at, when you are looking at last digit, that means you are going modulo 10. Right? So if you are working with integers, suppose our world of integers was not infinite, but only a finite world. We had numbers from 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. These were the only numbers which were available to us. And when you go next after 9, it would again send you back to 0. Suppose this was the case. Okay, the addition would still be there. 2 plus 5 will be 7. 5 plus 7 will be 12, which will be 2. So it's a group under addition. It's also a ring and so on. So you can add, you can multiply. This is the beauty about modular arithmetic, which is that you can do almost all the arithmetic. You can add, you can subtract, and you can multiply. Modulo every integer n. And therefore, if something should happen in the usual world of integers, it should happen in this modular world also. And turning this statement upside down would tell you that if something doesn't happen in this modular world, then it cannot happen in the usual world. So modulo 10, what are the multiples of 2? They are 2, 4, 6, 8 and 10. 10 is again 0. These are the only multiples of 2 and 3 will not come as a multiple of 2. Therefore, we have that 2023. Modulo 10 is not a factor of 2, but 10 is a factor of 2 and therefore 2023 cannot be a factor of 2. So this is the way one would use modular arithmetic. All right, comedy videos is saying good morning. So I think he is not in India right now, he or she. Right, so Ajay Zangal is asking, can we please explain question number 4 of assignment 4? Sure. So I think what I have explained to somebody else just now is that we will take other doubts for some time and then we will go through the questions that have been asked. Okay. So Kaustubh says that, sir, in a previous lecture, you used the clock analogy to explain congruences, which I found helpful. Are there other visual methods or analogies that make congruences more intuitive? So clock is the analogy that we have been regularly using even before we understand how a clock works, right? Meaning, I think if we go by the usual school standards, then maybe in standard 3 or 4, that is when we are taught how to read a clock, and therefore we are more used to clocks. But it's like going around and coming back and so on. That is something we are very used to. You can also work with clocks, but not think about the hours, think about the minutes. So you have 60, which there are 60 minutes, and supposing that there were no hours, but you were counting only the minutes. And whenever you are, 35 minutes are done, and after 35 more minutes, you will be at 10 minutes. Of course, the hour has gone next thing, but that is okay, that we understand, right? Because even in the clock, after if there are 17 hours right now and then you go to 10 hours after that, we go into the next day, but that we understand. So the same thing will tell you that you can use the clock to understand the congruence modulo 60 as well. And if clock is really the device that explains things well to you, then imagine a big clock for all the numbers that you have. Meaning, if you have to work modulo 100, imagine that you have a clock where there are exactly 100 numbers placed symmetrically. And then when you go to 100, you are at 0. And then you go ahead. So that is how one would go. So Chokita Bing, thank you very much for the compliment. Geeta is asking which books for reference. So the books for reference, I think there is this book by Alan Baker, Professor Alan Baker. He has written a very nice book. So there is a book called there are two books by Professor Baker. There is one book called A Concise Course in Math Number Theory. A concise course is something, concise meaning it is keep the volume of the material discussed is not very big. And then he wrote another book, which is a comprehensive introduction to number theory. So, or yeah, a comprehensive, I think comprehensive is there and number theory is there. It's there on our course webpage. So you can go and check it. These are the two books which I am following. But of course, from here and there, I take some proofs once in a while because sometimes, the proofs are given better in different books. And it is also some personal choice which comes in play. So I may have studied number theory from some book when I was a student, and I may have liked that thing very much. And so I may have taken some things from here and there, but this book of Alan Baker should suffice, really. Advik is asking, after this course, what should I study to read and work on papers by current number theorists? Well, Advik, very good question, like all other questions, of course. So, the thing is that, meaning, unfortunately, number theory is one of the very old branches of mathematics. So, the thing is that the thing we are studying now, we discuss Gauss and we discuss prime number theorem and we discuss Ramanujan and so on. So, these are some of the very old things which are more than 100 years old. Correct. But if you want to read what is done now, what you should really look for. So there are two ways to do this. First of all, meaning I would suggest that if you really are interested, if you are doing something else, if you're not a student or you would not want to be a PhD student somewhere, then and you want to learn it yourself, then I would suggest that you look at some of the expository articles. This is one great thing about mathematics, that there are some journals which are devoted to writing expository articles. They are the ones which expose people to some of the modern mathematics. And there are many such journals. There are many such things. So, what I would suggest is that you go through some of the current number theorist web pages. There is something called Number Theory Web. Number, Number, theory, Theory, and web, which is WEB. So you search on Number Theory Web. Number Theory Web has practically everything that is to do with number theory. So it will give people the list of people who are currently doing research in number theory. It will also list some of the notes on some of the topics in number theory. For instance, there is algebraic number theory, combinatorial number theory. We are studying basic number theory. But some years back, the basic number theory wasn't really basic. It was what is called the part of number theory that one should learn so as to be able to understand all the other mathematics. So, basic is a term which can be ambiguous, but algebraic number theory, analytic number theory, combinatorial number theory, transcendental number theory, probabilistic number theory, these are some names which quickly come to my mind. And these notes are available on the number theory web, and in general, you can get lot of resources there. So my suggestion would be to go to number theory web. Of course, another suggestion would be to join a place where there is a number theorist working, and then you learn from the number theorist. That's the best way, actually. So Kalyangiri is asking, the greatest common divisor of the integers a, b that are not both zero is the least positive integer that in a linear combination of a and b. Can you explain the theorem for us? Okay. So what was the result? The result was to show that the GCD of a and b is a linear combination of a and b. That's a great thing because, meaning we are saying that GCD is something which should divide both a and b. And you can actually get it in terms of a and b itself. That is really a very nice thing to have, meaning you don't have to go outside somewhere to find the GCD. So how do we do this? What we went through was that we looked at all the integral linear combinations of a and b. The combinations can have coefficients positive and negative. Meaning suppose I am looking at 5 and 3, then 2 will be there because 5 minus 3 is an integral linear combination of 5 and 3. Or 1 will be there because 3 into 2 is 6 and you subtract 5 from that. So 6 minus 5, 1, which is also there. So all these numbers, what we do is that you'll take all numbers of the type an plus bm. You let m and n vary over integers, positive, negative both. But this set now is a set of integers, so you can put it in order. There is 0, which is 0a plus 0b, and then there are some positive numbers which you have in this. So among them, you choose the least. Among the an plus bm, where n and m vary over integers, not necessarily only over natural numbers. In fact, not over natural numbers. Then you look for the smallest number in this, and then we prove in our theorem, in the proof, that this smallest will have to divide both a and b. And if it doesn't, then there is a contradiction to this number being least. So that's how the proof actually goes. Anshu is asking, sir, exam will be pen, paper or computer based. So, what happens is that typically in this exam, there are, for this course, if you have gone and seen, there are about a few thousand students who have registered. And though all of them don't register for the exam, I think there is easily the number goes more than 100. Because people would want to come and learn, but giving an exam and getting a degree or certificate out of that is not something that everybody wants, which is fair enough. Right? So there are still 100 or so students who take the actual exam. And then it becomes difficult to go through all the answers and grade them. So we have resorted to a computer-based exam. So what it says is that there will be problems given to you on computer and the answers are to be the answers are to be keyed in. You have to type the answers or from the given choices, you have to choose the correct answer. So it will be like, if there is a 2-digit number which will be answer, then you will have the tens digit, there will be 10 choices. The ones digit, there will be 10 choices. So if the answer is 21, you have to choose 2 from the first choice and then 1 from the second choice. That will give you 21. Or I don't know how the exact way is, how the exact platform works, or maybe you should type 21 and then that would be taken as the answer. So this is how it will happen. But I believe that you will have pen and paper available for you to do some calculations that you want to do. It is not expected that you will think in your head for all the calculations. So you will have pen and paper with you. Okay. Ruturaj is asking, are those above students studying in IIT B? So Ruturaj, which ones do you mean by above students? People who have asked questions above me? Meaning people who have asked questions here before? No, I don't recall any of them. Meaning typically, IITB students would come to me and discuss with me, so I would remember their names. I don't recall any of these names. ABCD is asking another question. Does mod 0 exist or is it not allowed in modular arithmetic? I scratched my head on this in question 5 and 8, assignment 3. Mod 0 doesn't exist. Because when we talk about mod n, we will have exactly n elements. We will go from 0 and go up to n minus 1. If there is mod 0, then we cannot work with mod 0. It's also the division algorithm in a way. Because what is mod n? If you are saying that some number a, which is an integer, is congruent to b mod n, and b is between the modular, the reduced residue classes that we are looking at, then we are looking at division algorithm in the other words. But division algorithm doesn't hold when you are trying to divide by 0. So mod 0 doesn't exist. Mohini Kadam has written Alan Walker. No, it is Alan Baker. ALAN and BAKER. Baker, somebody who will bake cakes for us. Geeta has asked for books reference and Mohini has kindly typed the name, but it should be typed as Alan. I believe the spelling is ALAN, then space, and then Baker. B for Bombay or B for whatever, ball or a bat. Baker, BAKER. Okay, so ABCD says, luckily I got the answers of both correct on the basis of your lecture. I am pleased. SM is number theory important for NET exam? I have not set exam papers for NET in quite a while, so I cannot comment on that. Krishna Nayyar is asking another thing. Sir, I am talking about 3x plus 1 conjecture. What is called power n capital N, where n is this, where p is the immediate predecessor of capital N, as n and n are sufficiently large. Correct, Krishna Nayyar, when you said collards, that's the thing which would come to my mind. So maybe I can tell what is the 3x plus 1 conjecture, although I think I have discussed this in my lectures also. So what it says is that, it's a function defined on natural numbers. If you take a natural number, if it is even, you divide it by 2. And if it is further even, you continue dividing by 2. If you reach odd number, then you multiply by 3 and add 1. So my favorite sequence in this is starting with 5. When you look at 5 into 3 plus 1, that gives you 15 plus 1. And 15 plus 1 is 16. So 16 gives you 8, 8 gives you 4, 4 gives you 2, 2 gives you 1. 1 is odd. So 3 into 1 is 3 plus 1 is 4, 4 gives you 2, 2 gives you 1. So this 1, 4, 2, 1 is what is called a loop. If you reach 1, then you will be in this loop. And 3x plus 1 conjecture says that whenever you start with any integer, you would come to this loop eventually. And this is not yet proved. This is not yet disproved. There is no answer known on this. And in fact, one very famous mathematician by name Paul Erdos, had said that this problem is devil's work. These are created so that the mathematics progress should be stalled. The mathematics should not proceed. The mathematics should not progress. That is what some people want. And therefore, such problems have been created. But this is a very difficult problem, notoriously simple to explain, yet very difficult to crack. Many great number theorists have worked on this. All right, so call power n, Krishna Nayyar, I unfortunately don't understand this notation. I understand that, so you are taking n and capital N to be very large, and p is taken to be immediate prime predecessor of capital N. So you have 2 power n, 3 power n, 5 power n, up to p power n. You have a huge number which you call capital N, right? And you are asking n equal to this. So you are starting with small n, and I suppose you are taking p to be the prime before small n, not capital N. And then you are writing this capital number n, which is obtained by 2 power n, 3 power n, so on up to p power n. But then what are you going to do with this is not clear to me. Are you suggesting a different way to state Collard's conjecture? That I don't know. Okay, Fazila has asked another question. Could you please discuss discrete logarithm? Okay. So, what is logarithm? Logarithm is something when you have a power n equal to b, then we would say that this power n, we want to capture that power, right? So, we will say that n is log b to the base a. This is what you would say, right? So, log of e is 1, log of e square is 2, and so on, right? So, the discrete logarithm, it's a way to encode things. What happens is that given the it comes back to modular arithmetic. It is easy to take products in modular arithmetic because you will just take products and you will go modulo the whole thing. And it's also easy to do addition, subtraction, and so on, because when you take AB and you may take their powers, taking powers is like again taking product. And then when you are applying the division algorithm, or you keep subtracting multiples of n from that, division is a bit difficult than taking product. Addition and subtraction are the same. Multiplication is simpler, but division is a bit difficult because you have to go through many steps to apply division algorithm, to apply division. But even that is okay. The worst thing is taking a certain root. Meaning, given a number, if I were to ask you to compute root of that number, then that would be very difficult to compute. Which is this taking root is something like taking the discrete logarithm. So what happens is that when we want to encode something, you can simply put it as power of a fixed number and send the encoded message. And to decode it, the receiver should know how to decode it by knowing what the number, what the base was used, and how the power thing was used. Okay, so that is the way one could encode it. But decoding will be difficult because if I'm given that my number is a power of n, then what power it is, that would be very difficult to get, especially you are working with modular arithmetic, because in modular arithmetic the powers can be really very strange. Like we are discussing in this assignment, the powers of 4, when can they be 1 modulo 7? We know that 4 is 4, 4 square is 16, which is like 2 modulo 7, and 4 cube, which will be 4 into 2, that would be 8, that is 1 modulo 7. So 4 cube is 7. Therefore, 4 cube is 1 modulo 7. So if I were to ask you what is the power of 4, which gives me 1 modulo 7, the answer can be 3 and the answer can also be 6. So there are two, of course, solutions to this. But, even if you were working with a number which is a primitive root, for which then there will be a unique answer. Even for that, getting that particular answer is difficult. That is what makes the whole thing difficult. So that's in a way some answer for this. Fazila, Ruturaj is saying that, sir, right now I'm a JE aspirant, will attend the JE 2025. I have got a huge interest in maths. Can you please tell me some reference books for maths calculus? So mathematics calculus, if you want to study calculus, there is a mathematician by name Walter Rudin. He has written many books on analysis. Calculus is the beginning steps of analysis. So you can search for Walter Rudin, and then it will tell you there are many books. There is something called Baby Rudin, which is Principles of Mathematical Analysis. This is typically a book which all first year students who come to IIT Bombay and want to really study mathematical analysis from a strong viewpoint, from theoretically very strong, they are this is the book that they would go to. Okay, Kaustub Kambli is asking, sir, will we have proofs in the exam? Will we just have sums of applied nature like the ones we have in our assignments? There will be no proofs, because again I cannot go through all those 100 plus answers. So there will have to be some computer gradable questions, and those are possible only when we have sums. So there will be only sums. Okay, Krishnan Nair has again explained his. Sir, for example, call square is call of call n, applying call 2 times. If capital N is 3, call square of 3 is 5, because 3 into 3 is 9 plus 1, and you divide it by 2, so you get 5, correct? I have started with capital N and small n, and take n as above. Actually, I'm working on this notorious conjecture. Very good, Krishnan Nair. I will wish you best luck. But we cannot discuss it here. What you are trying to say is that, okay, so you have a capital N and you want to know what is the call n power n. You are applying Collard's operator n times to these numbers, and you are looking at where it goes. Good. I suggest that you keep working on it, and we hope to see a proof sometime soon. Okay, I think I don't see any more questions. So let me now go to the questions which are asked in the assignment. So we will go assignment by assignment. There is maybe still about 15-20 minutes left. So let me just quick if there are anything from assignment 0. So as of now, there is something from assignment 3. After that, it is assignment 3 again. Previous assignments, I guess, Shashya, Shashwat, Shasya, Shaswat, but we have answered already. Assignment 3 again. What are the divisors of, okay. So this is the question which Kapil Kumar has asked. So if you take I power I and then take the power of this whole number, he has asked me what are the divisors of this. So this is an easy question and therefore I can answer it right away. The divisors of I power I or any, if you take a number n and you take its powers, the divisors of this number are can be written in terms of the primes. So first of all, for any number n, the all divisors can be written in terms of prime factors, and the prime factors of I power I are the prime factors of I. So once you suppose you take I to be 20 and you take 20 square, which is 400, which will be 20 into 20. So it will be the product, the primes which appear in 20 and again the same primes, only that the superscript, the index will be multiplied by 2. So I power I, the divisors, the number of divisors can, once you have all prime factors and all exponents of those prime factors, then you can write down the list of divisors. All the divisors will be of the form, suppose your n is p1 power a1 up to pk power ak, then every divisor of n is of the form p1 power b1 up to pk power bk, where bi start from 0 and can go up to ai. This is the set of all factors of this. Okay, so somebody says that many questions are marked inaccurately in assignment 3. Okay, we will come to that. All right, so there is this question. Kaustu has asked a question here also. He says, hello, I am a graduate student in statistics. After working in the industry for a year, I have decided to switch to pure mathematics because of my strong passion for the subject. I have two questions. Beyond self-studying core subjects like linear algebra, real analysis, and topology in an appropriate order, is there anything else I should focus on to prepare for a master's degree in pure mathematics? Yeah, meaning you have lost on one very important concept, which is the differential equations. There is group theory, etc. If you want to do masters in pure mathematics, you will need to learn quite a lot. Typically real analysis, linear algebra, and in a bit some topology. Topology is a part of MSc, of course, but the other two that you have talked about are really BSc courses. So for MSc, you would need to learn quite a lot. And he further asked, additionally, is a transition from statistics to pure mathematics feasible in theory? Of course, it is possible. Meaning people have come to mathematics from physics background, chemistry backgrounds. So coming from statistics background is the easiest thing, I would say. Of course, it could also be slightly difficult in the sense that statisticians are taught to think in a certain way, and to do mathematics, you will need to think in a different way. So that could be the only thing which would hamper. But otherwise, I think if you are really willing to put in efforts, then it should work out. Also, he says, currently I am studying real analysis, abstract linear algebra, and discrete mathematics through books, along with basics in number theory through your lectures. As I progress, I understand that mathematics is a vast field. I couldn't agree more. And eventually, I will need to specialize. Should I first build a strong foundation across multiple areas of mathematics before choosing a specialization? Or is it advisable to explore only an overview of various fields and select a specialization early on to save time and energy? Good question again, like many other questions that everybody has asked. All right, so whether you should study everything or whether you should specialize, this is the question that is asked here. My answer would be that you don't specialize until you really have to. Meaning, supposing that, if you are studying for some masters or you are enrolled in an institute, I am assuming that you are enrolled. If you are not enrolled and you are doing something else, you said that you are working in an industry and you are perhaps reading mathematics on your own. If you are reading it only for pleasure or to enrich yourself with mathematics, then you are fine. You could just, specialize, choose a topic and read as much as you want. If you get bored with that, go to another topic and read it again from the basis. That would work. But if you want to, make a career out of it, if you want to study mathematics, if you want to do PhD in mathematics, then there is typically a time limit. So what we should then do is that, we cannot keep reading everything. you have also rightly pointed out that mathematics is indeed a vast field, and therefore reading everything that is basic will not be possible. So what we will do typically in every mathematics department, we identify some areas as the important areas compared to other areas, depending on our personal choices, of course. So those areas are called important, and we will teach that mathematics in the MSc program. If you go to another department, it is likely that some other things will be deemed important because their choices will vary. But what we have at least tried to do is that, if you are going to any of these institutions in India or abroad for PhD, then you would be able to learn you will be able to learn the research areas using these things. So there is typically a mathematics MSc level syllabus which is available for most of the IITs. You can come to IIT Bombay Maths department and check the MSc syllabus. I would say that that is a very standard syllabus as the level of foundational courses go. Of course, the MSc is for 2 years. So there is the first year where we have core courses which are compulsory for everybody. And in the second year, then courses become elective. Elective means that this is a knowledge which is perhaps not required as the courses in the first year are. So I would suggest that you come to IIT Bombay Maths Department website, look at the syllabus and check the courses in the first year. And if you can master that, I think you will be really very well placed to jump into mathematics. So good luck. All right. Okay, so there were questions about questions. So there are assignment questions. Before that, there are other questions here. ABCD is asking, can you please outline the eligibility of NPTEL internship as in what type of topper? Topper is basically, there is a score from assignments. I think the out of 12, as I said, some 8 or 9 are selected. That is given some weightage, perhaps 60% weightage. And then whatever score you get from the final exam, that is given 40% weightage. Combining will give you a score. So for instance, out of these 12 assignments, your top 8 assignments out of 80, suppose it amounts to 76. Then this 76 is out of 80. So we will convert it to out of 60 to a number. And then in the exam, suppose the final exam is for 55 marks and you score 35 marks in it. Then this out of 55 will be converted into out of 40. And then that score plus this score will be added to give a score out of 100. So now once we have numbers, once we have scores with the common denominator 100, we can see who are the toppers. And then the toppers are offered to do internships. So this is the internship eligibility. I think the other eligibilities will be that you should, typically have some degree certificate and so on, whichever is required for the corresponding courses. So those are the eligibility things. He says he is an AIDS student, so I wonder if I can take an internship of it. That I don't know. You will have to ask somebody, meaning not me. Sharanya Vinod is asking, while submitting assignment for this course, we have multiple answers. For the certificate exam, the answer will be a single answer or multiple answers. Need a clarification regarding this. So to tell you a secret, I have not yet prepared the final exam. And so far I have been giving only the answers which are single answers, in the sense that I will say that there are 3 possible answers for this and write the smallest answer here. There will be a space for writing the smallest answer. Then there will be the space for writing the next smallest answer. And then there will be the space for writing the other answer. So, if the answers were 2, 5, and 11, then you should, in the first slot which is given to you, you should write the answer 2. In the next one, you should write the answer 5. And in the next one, you should write the answer 11. But there won't be too many answers. So don't worry about that. Also, multiple answers, the thing is, why do we have multiple answers? The reason for having multiple answers is as follows. Suppose the question is what are the numbers which satisfy a particular property, and while checking it, if the first number satisfies the property, people often tend to check only that. They don't check the remaining ones. That is what we have found. So we want people to do all these calculations, meaning, unless you really sit down and do these calculations by hand, you are not going to understand this mathematics. We all watch cricket matches on TV, but we don't become Sachin Tendulkar, Virat Kohli, or Rohit Sharma because we are only watching it. We are not doing it ourselves. So if you watch only the videos of Shripad Garge on basic course on number theory, and if you don't do it by hand, then forget about becoming Shripad Garge. I think even understanding the basic course in number theory will be a bit difficult. So we want people to do all these calculations. And meaning if you are able to see my videos online and so on, you have access to a calculator. That is what I would believe. And then meaning sitting down and doing half an hour work every day should be enough to check two answers. You have to solve two questions in half an hour. 15 minutes per question is not really very difficult once you get a hang of it. Remember how we started our basic questions in the assignment 1 and 2 were simple, and only now we have gone to higher numbers, right? So doing this by hand is not maybe difficult. For some people, it may take 1 hour, but this is the course that you have opted for. So giving meaning in addition to watching videos, say for 2 or 2.5 hours per week, giving 1 more hour is like spending less than 4 hours per week on this. So, I think it should not, okay, so not giving 1 hour, maybe 1 hour for two problems, so 3 or 4 hours. But so it will be like 8 hours per week on a single course. This is how you would spend the time in usual studies as well. Right. So I think, trying to do all these problems by hand is not a bad thing at all. So please try these problems. But anyway, to answer your question, Sharanya, there will be unique answers in the final exam. Abnish Kumar Verma is asking, sir, I am currently studying group theory. Can I continue number theory? Will it be helpful? Of course, it will be helpful. Group theory is useful in number theory, and number theory also gives you lots of examples in group theory. Meaning in group theory, there is something called representation theory, which is the representations of groups. If you are working with finite groups, there is a branch of number theory, which is called algebraic number theory, which will be very useful in doing representation theory. Okay, Fazila has asked another question. What is the remainder of I power I is divided by 10? So it depends on what your I is. Also, you should know where you are putting the brackets. So I think my question was, I had put brackets for I power I. There was a bracket and then there is a power, ith power. If you are looking at only I and then you are taking its power, which is I power I, then that's a different number. To give you an example, if your I is 3, so you are looking at 3 power 3, which is 27. And then you are taking the cube of it. That's a slightly smaller number, right? It's 27 cubes. So it is between 800 and maybe 620. Yeah, it's a number which can be managed by hand. But if you take 3, put a bracket, take the power, which is 3 power 3. Then you are taking the 27th power of 3. These two things are different. 3 power 3, whole power 3, which is 27 power 3. And 27 is already 3 power 3. So what you are going to get is 3 power 9 because you have taken 3 power 3 and the cube of it will be taking this number 3 times. So you will write 3 power 3, 3 power 3, 3 power 3. So you will add the exponents and you get 3 power 9. Whereas in the other form, when you put 3 and then put the bracket for the exponent, you are getting 3 power 27. So it is important where you put bracket. And in my question, I think in the assignment, I had put bracket in the number below because I don't want you to do this 3 power 27. I want you to do 3 power 9. So you should work with 3 power 9 and check what the remainders are. That would then be easier. Okay, I think there is almost time. So to answer once again, there are these questions about assignment 3. So I have already answered in assignment 3. Can I go take 5 more minutes? I believe I can. Nobody has said I cannot. So this is what the 10th problem is. The remainder of I power I, that to the power I. when divided by 10, right? So, of course, what are the possible reminders? Also, the thing is that the remainder can be. So when you say the remainder can be, it means that the remainder can be 1, the remainder can be 2, 3, all these possibilities are there. But when we say that the remainder is, then there is a unique answer. And this is, I think, a doubt for many people in some question in assignment 3, where I have said that, if you have, if A in Z mod 27 is a solution for 6x equal to 3, then, and when you say then, if I say A is equal to 5, that means A has no other way to get the solution. A equal to 14, if A equal to 5 and A equal to 14, these will not be consistent choices. The consistent choice would be that A is in the set 5, 14, 23. We have to give a definite answer, because A equal to 5 just means A is equal to 5. And that is will say that that is the definitive answer. There is no can be. There is no way to allow possibility for other answers. That is why the assignment 7 in the question 7 in assignment 3 has been marked in that particular way. So coming back to this I power I, if you take I equal to 1, then you get 1 power 1 power 1, that is 1. So you get 1. If you get 2, 2 square is 4 and 4 square is 16. So 6 is a possibility. If you take 3, 3 power 3 is 27, which is like 7, and 7 cube. So 7 square is 49 and 7 cube then will be something 3. There will be the last digit will be 3, which is there. And these are the only possibilities, I think, if you look at it otherwise. So, 4 power 4 will be 4 square 16 and its square is again 6. And then the 6 has the property that any power of 6 has only 6 in it. So 6 has already come. For 5, the answers will always have 5 in the last digit. 6 I have said already, and 7 is minus of something. So 7, 8, 9, you can work with taking the negatives. So we are almost running out of time. Let me just quickly check what are the things that we have seen. One more question. Does the topper of MSc Math student get medal? I think there is no physical medal, but you do get a certificate saying that you are among the gold standard students or something. So the certificate has some gold or platinum or some such word written on it. Fazila is further asking, how is number theory related to cryptography? I cannot answer that right now. And somebody in Urdu or Arabic whose name is asking, sir, does the assignment marks count towards the final exam? In the final exam, the marks are not counted, but when we take the final score, these marks are counted. But again, as I said, not all assignments. We take some top 8 or 9 assignments, the scores that you have done, and we convert it into 60. And then again, the final exam score is taken out of 40. So, all right, I think it's a good time that I had. We will have one more such interactive session next month. I look forward to that and see you again.